Now let's look at groups of order p times q, where p and q are primes and p is less than q. Now let's look at the possibilities for nq, the number of Sylow q subgroups. Well, it has to be congruent to 1 mod q. And yet it also has to divide p. And the divisors of p are either 1 or p. And so given that q is bigger than p, well, as soon as k is 1, 1 plus kq is too big. So we see it must be the case that k is 0. So nq is 1. So we see in general that the number of Sylow q subgroups is 1. And so if you let q be a Sylow q subgroup, then it's actually the case that q is normal in G. And of course q is cyclic. Well, now let's look at n sub p. Well, it has to be 1 plus a multiple of p, and it also has to divide q. Now, of course, this argument no longer works because it's possible that some multiple of p plus 1 is a divisor, is equal to q. So you're either in two cases, either n of p is equal to 1, or you're in the case that n plus p is actually equal to q itself. In this case, that means that q must be congruent to 1 mod p. So that could happen, depending on p and q. The easiest obvious example is if q is any odd prime and p is 2. Well, any odd prime is congruent to 1 mod 2. But if you want something slightly more non-trivial, if q is 7 and p is 3, then 7 is congruent to 1 mod 3. So these types of cases can happen. So we'll deal with that case separately, but the first case, if np is 1, and you let p be this normal Sylow p subgroup, then p is also normal in G. And since p has size p and q has size q, and p intersect q has to be a subgroup of both of them, whose size divides both of them, that size is 1. So by the diamond isomorphism theorem, I forget which name it's given in this book, but so I'm going to call it the diamond isomorphism theorem. You have to have PQ is a group, and what is its size? Well, it has to have size P times Q. Oh, it must be all of G. This textbook hasn't talked about direct products yet, but from an undergraduate course you might recognize that in this case, when you actually manage to write G as HK, and H intersect K is the identity, then it is a fact that G is actually isomorphic to the direct product of H times K. So in particular, G is actually isomorphic to ZP times ZQ. And it's another fact from the theory of direct products of cyclic groups that since P and Q are prime, that is just the cyclic group ZPQ. So in this case, you end up with a cyclic group. And this is one way to see that through other theories about direct products. That's worth trying to remember. If you don't like that approach, the textbook uses a different approach where they point out that G mod Q or G mod P, it doesn't really matter which you pick, is cyclic. And then they do an argument like I did in the last video, where you take the cyclic generator, some power of it lands in Q. You end up arguing that you get commutativity, and then you get an element of order PQ. Of course, the other case is that NP is equal to Q, that you have Q P subgroups. And we already dealt with this in the previous video when P was exactly 2 and we got the dihedral group. So it's a good question in general. Do you actually get something interesting? So, with 7 and 3, so groups of size 21, is there this non-trivial group going on where you've got a normal subgroup and the quotient is isomorphic to Z mod 3, but it's not the direct product, because that was covered in the previous case. The book actually does give an argument that such a group exists, but it relies on an exercise from a homework assignment that obviously we haven't done. And it's not quite necessary, because in the next chapter they actually do define this group a different way. And in the different way, it's actually isomorphic to what's called a semi-direct product. And so we're not going to define semi-direct products yet, because we're not there yet, but it does turn out you can do this. And so the main ingredient in a semi-direct product you need is an automorphism. And it turns out there is a good automorphism. So phi of 1 takes the element 1 and sends it to 2. And you can check that phi 1 squared is 4. Phi 1 cubed then would be 8, which is 1 mod 7. And so you see it sends the generator to 1 mod 7, and so phi 1 cubed is the identity map, so this operation has order 3. And so of course you see what phi of negative 1 has to be in order for this to actually be a group operation. It's going to be the one that sends 1 to 4. And then you do get this automorphism. And in general, when you're in this setup where Q is congruent to 1 mod P, that means that Q minus 1 is a multiple of P. And we remember that the automorphism group of ZQ has order Q minus 1. This tells you that there is an element of order P in this automorphism, which means that there actually is a cyclic group, a copy of the cyclic group, CP, sitting inside this automorphism group. So you can actually construct such a group homomorphism, which we will need later when we talk about semi-direct products. So it will turn out it is possible to have such an automorphism, and so you can actually construct such a semi-direct product, and so it does turn out in general that such a semi-direct product does exist and is unique up to isomorphism. Of course, it's kind of cheating because it's relying on undefined definitions. What we can conclude for right now is that, as we had previously, P times Q is equal to the entire group. Q is normal in G, and P intersect Q is the identity. That's all we know for right now, is that if such a group exists, it has these structural properties. And then later in the chapter on semi-direct products, we'll discover that these properties happen if and only if G is isomorphic to a semi-direct product of P and Q. And so then it turns out that such a group exists if and only if you could write it in this manner. And then this theory here, that this automorphism exists, tells you that this construction actually does happen for any P and Q where Q is congruent to 1 mod P. This also tells you why this doesn't happen if you don't have this condition. If you don't have this condition, no such automorphism exists. And since no such automorphism exists, this semi-direct product construction doesn't work. The only thing you could do is the trivial homomorphism that sends Z3 to the trivial subgroup, and that just gives you the direct product back again that we already covered. So now we're going to make things slightly more interesting. Since we just covered what happens when you multiply 2 distinct primes, let's talk about multiplying 3 distinct primes. But let's make our lives interesting by picking the simplest case. The smallest 3 distinct primes there are, 2, 3, and 5, so that's groups of size 30. What can we learn about groups of size 30 just by looking at Sylow subgroups? Well, we see N5 has to be a divisor of 6, and has to be congruent to 1 mod 5. So there are 2 choices. It's either 1 or it's 6. So in one case you get something normal, in the other case you get something that's not. Similarly, N sub 3 is going to be congruent to 1 mod 3, and it has to divide the product of 2 and 5, which is 10. And so the only possible choices are either 1 or 10. Again, in one case you get a normal subgroup, in the other case you don't. And so now we're going to start talking about what happens when you get in these cases. So what happens if N5 were 6? This is an idea about what you can do when you've got multiple subgroups of prime order. So these types of arguments are only going to work when you have a prime. So this isn't going to work if I had a 5 squared, but it will work because I have 5. So this says I have 6 subgroups of order 5. Notice that when you have 6 subgroups, that means I have 6 copies each one has 6 elements. But not all elements are created equal. That's really one element of order 1, the identity element, plus 5 elements of order 5. Of course, whenever you intersect any of these 2 groups, you're going to get a subgroup. But these groups are distinct, so what subgroup do you have to get? You have to get the trivial subgroup. Which means these 5 elements of order 5 in P1 have to be different than the 5 elements of order 5 in P2. In particular, this means that you see that we have 30 elements of order 5. So in general, when you're in these cases, you actually can start to get a count on how many elements you have of that prime order. If your group isn't normal, if your your Sylow P subgroup isn't normal, and if your Sylow P subgroup has order P. If it has order higher than P, you have to be a lot more careful because then these intersections aren't necessarily the identity. Similar arguing, 10 times 2, there might be 20 elements of order 3. Maybe. Scratch that, I got one of these calculations wrong. This should be 4 elements of order 5, right? So that should be 24. So 24 is less than 30. That's not a problem by itself, as is 20. But we see if we combine these two numbers, you get something too big. So 20 plus 24 is bigger than 30. And so what we can conclude from this is that n5 equal to 6 and n3 equal to 10 can't both be true. So just by looking at the numbers, the prime factorization, and doing these calculations, we've actually ruled out a possible case of subgroups that could happen. It is never the case that you have 6 Sylow 5 subgroups and 10 Sylow 3 subgroups. And this happens in classification type results. You have to rule out things as saying that there's no such group with these types of properties. What does this tell us? This tells us that it must be the case that either n sub 5 is 1 or n sub 3 is 1. In other words, if you let P be a Sylow 3 subgroup and Q be the Sylow 5 subgroup, one of them must be normal. And so you will find these types of arguments to be useful. If you're trying to prove that there's no simple group of a certain order, you have to use Sylow theory type arguments to prove that one of these things has to be 1. And that's what we just saw. We can now conclude there's no simple group of order 30 because one of these two numbers must be 1. Of course, we can go a little bit further. Since P intersect Q is the identity element, by the diamond isomorphism theorem, PQ is in fact a subgroup of G of order 15, which means that the index of PQ and G is 2. And that means there's exactly 2 cosets. And it's not too hard to show that if there's exactly 2 cosets, then your group must be normal. So we see that not only is there a normal subgroup of order 3 or 5, we don't know which, but we see that there must exist a normal subgroup of order 15, which is 3 times 5. Oh, but by the previous calculations, a normal subgroup of order 15 is either cyclic or this other weird construction, and that weird construction only happens when Q is congruent to 1 mod P, or the larger prime is congruent to 1 modulo the smaller prime. That doesn't happen here. So by the previous case we just discussed, N is cyclic. So just by studying Sylow theory, we've now determined that every group of order 30 has a normal subgroup that is cyclic and of size 15. So this tells you the power of these types of theorems. I mean, if you wanted to classify all the groups of order 30 up to isomorphism, you now are halfway there. I mean, you know that there must be a cyclic group, and you know that the quotient is obviously Z2. And N is isomorphic to Z15. So now you're just asking yourself, how many ways can I construct a group? Can I construct a group with a normal subgroup that's isomorphic to Z15 whose quotient is Z2? If I can solve that problem, I've now constructed all the groups of order 30 up to isomorphism.